All right, guys. So let's talk about investigating symmetry. Okay. For the learning target for this section, I can determine whether a figure has line of symmetry or rotational symmetry. A figure has symmetry if a rigid motion exists that maps the figure onto itself. So if we look at the picture to the right, we can see this triangle, and we can see that if we reflect it over this vertical line, okay, that the triangle is going to fall on itself. Okay, so it's going to be the original triangle. So that's what we call a line of symmetry. A figure has line symmetry or reflectional symmetry if a reflection maps the figure onto itself, just like it happened with the triangle on the right. And also here, if we think about this half moon, okay, we could draw a horizontal line, and we can see that if we were to reflect it, it would just get flipped, and then the moon, the half moon will just fall on itself, okay? So basically, if the figure maps onto itself, then it's a line of symmetry. It's a reflectional symmetry. Let's look at this first example here. So we have these three images, and we're trying to figure out how many lines of symmetry it has. So if we think about a rectangle, we can kind of like draw a vertical line through the middle, and that would be one line of symmetry, because if we were to flip it, the rectangle would fall on itself. And then we can also draw a horizontal line, and that will also map the rectangle onto itself if we were to flip it horizontally. So that there are two lines of symmetry in this case. The triangle here, this is a scalene, which means all the sides look, they're different sizes. So this one has zero lines of symmetry. There's nowhere where you can draw a line and then reflect it, and then the triangle would fall on itself, and it would have the same image, at the end. Now, if we look at this other shape here, it's kind of like an L, right? If we were to draw a line on a diagonal and flip it over that line, reflect it over that line, we can see that it's just going to fall on itself, and we're going to end up with another L. The same image will appear. So we have one line of reflection in this case. Okay. Let's check rotational symmetry. So now we're talking about a figure. If a figure has rotational symmetry, right? It has rotational symmetry if a rotation maps the figure onto itself. So again, we're rotating a figure and we're mapping it onto itself. So that means it has rotational symmetry. Um, if we look at this star over here, if I were to rotate it, right, as the arrow is pointing to the left this way, I can see that I would have another star, right? If I rotate it once, I would fall right on top of that star. So it means that this image has rotational symmetry. The angle of rotational symmetry, which is greater than 0, but less than or equal to 180, is the smallest angle of rotation that maps a figure onto itself. An angle of rotational symmetry is a fractional part of 360. So for example, if we think about this star again, I can rotate once and it falls on itself. And then I rotate again and again, it falls on itself. And again, 5 times. So if I rotate this 5 times, I go back to the original picture, right? And I fall and the picture falls on itself 5 times, okay? So what I do is I do 360 divided by 5, and that is equal to 72 degrees. That means that every time you rotate this picture 72 degrees, it's going to fall on itself. Okay, so the angles of rotation here are 72. Then if I add another 72, that angle of rotation would be 144. Then if I add another 72 degrees, that angle of rotation would be 216. And then if I add another 72 degrees, I go to 288 degrees. And if I do it again, 72 degrees, I go back to the original. That would be the 360 degrees. Look at an example of rotational symmetry. So let's look at these three figures and decide the angles of rotation, okay? All the angles of rotation less than 360 degrees. If I look at a square, okay? Remember, the square has all equal congruent sides and angles. So if I rotate it to the left, I go back to its original picture, and then again and again and again. So I can rotate this 4 times and I go back to the original picture, okay? So if I do 360 divided by 4, I get 90 degrees. That means that every time I rotate this picture 90 degrees, I go back I go back to the original picture. So the angles of rotation here are 90 degrees. Plus 90 would be 180 degrees. Plus 90 is 270 degrees. The triangle that we looked above is the same one. There's no way I can rotate this and go back to the original unless I rotate it 360 degrees. Okay, so this is none. Okay, there's no angle of rotation less than 360. And if we look at this arrow, I can rotate it up and then I can rotate it again down. So that's 360 degrees divided by 2, and I end up with 180. Okay, so if I rotate this arrow 180 degrees, it falls on itself. Okay, and I get the same shape. Let's look at the types of symmetry here for this star. For this star, if we look at the types of symmetry, I can see that I can draw a line through the leg here, right? And I can draw another one through this leg, and I can draw another one through this leg. Those would be lines of symmetry, because if I reflect it over that line, across that line, I would go back to the original figure. Also, if I rotate, I fall on the star will fall on itself. And if I rotate again, I'll get the same image again, and then again, the same image. So that means that it also has rotational symmetry. And there are 3 lines of symmetry, 1, 2, 3. And the angles of rotation would be 360 degrees divided by 3, because it's 3 times that I rotated, and I get 120. That means the angles of rotation are 120, and then 120 plus 120 would give me 240. So those are my 2 angles of rotation. So guys, there are 4 problems. Let's see, 4 problems for you to try on the next page. And I also have some videos that you can watch on rotational symmetry and reflectional symmetry on your template, and also in the communication plan.